All right, let's start with something seemingly simple. Imagine you have a billiard ball. How many other identical billiard balls can you arrange so they're all touching that central one?
It sounds straightforward, doesn't it?
Hmm.
But this little puzzle is the heart of what we call the kissing number problem. Sometimes it's also called the Newton number.
Right, the Newton number.
Yeah.
So the mission today, explore how this basic geometry question, the maximum number of non-overlapping spheres touching a central sphere, gets, well, incredibly complicated in higher dimensions.
It really does. It starts simple, but the complexity ramps up surprisingly fast.
Before we dive deeper, though, we need to thank our sponsor. This exploration is brought to you by embersilk.com. If you're looking into AI, whether for education or integrating it into your systems, Embersilk really is the answer.
They make understanding and implementing AI much more accessible. You can find out more at embersilk.com.
Okay, so the basics. Let's start easy. One dimension, just a line.
Well, on a line, it's trivially two, right? One sphere on the left, one on the right of the central one. Can't fit anymore.
Dead simple. Now, two dimensions. Circles on a flat plane.
That one's 6, and we know it's exactly 6. There's a neat geometric proof for it.
How does that work?
Well, think about the centers of the circles. Since they're all identical in touching, the angle between the centers of any two touching outer circles, as seen from the central circle's center, has to be at least 60 degrees.
Ah, right. Because you form equilateral triangles between the centers.
Exactly. And since there are 360 degrees in a full circle, and 360 divided by 60 is 6, well, you just can't physically squeeze a 7th circle in there without overlap. The geometry locks it down.
Okay, that makes sense. Now, 3 dimensions, our familiar space. The answer here is 12, but I understand this wasn't always agreed upon. There was some drama.
Oh, absolutely. Big disagreement, actually. It was between Isaac Newton and the astronomer David Gregory back in the 17th century. Newton correctly figured it was 12.
But Gregory thought,
Gregory suspected you might be able to fit 13. And honestly, you can see why he thought that. When you arrange 12 spheres, they fit snugly, but there's still quite a bit of wiggle room. There are these small gaps left over.
it looks like there should be space for one more.
Precisely. It's visually deceptive. Proving mathematically that a 13th sphere definitely cannot fit without overlapping took, well, ages. The first fully accepted proof didn't come until 1953.
Wow, nearly 300 years later. And that number 12, it's not just theoretical, is it?
Not at all. It's actually super important in material science. It corresponds to the maximum number of nearest neighbors an atom can have in very dense crystal structures, like cubic close packing or hexagonal close packing. Think metals like copper or gold.
Fascinating. Okay, so what happens when we leave familiar space? 4 dimensions.
Things get even trickier. The kissing number in 4D jumps up to 24, and proving that only happened quite recently, in 2003. Oleg Musin finally settled it.
So before 2003, it was uncertain.
Yes. For a long time, mathematicians knew it was either 24 or 25. Again, that ambiguity persisted because proving impossibility is hard. Musin's proof involves some pretty complex geometric and algebraic arguments in 4D space.
And beyond 4D, I hear there are some dimensions where we do know the answer, and the numbers are huge.
That's right. There are these 2 incredible outliers, dimensions 8 and 24. They're special because they possess these remarkably symmetrical structures called lattices.
Lattices, like mathematical crystals.
Sort of, yes. In 8 dimensions, there's something called the E8 lattice. Because of its unique properties, we know the kissing number is exactly 240.
240, that's a big leap from 24.
It is. And then in 24 dimensions, you have the Leech lattice, which is even more extraordinary in its symmetry.
And the number there.
Prepare yourself. It's 196,560.
Whoa, okay. That's staggering. So these special lattices make it easier to solve.
Immensely easier, relatively speaking. The symmetry basically provides a perfect arrangement and allows for a proof. But for most other dimensions, like say dimension 5, we don't have these magical lattices.
So for dimension 5, we just don't know.
We don't know the exact number. We have bounds. We know it's at least 40 and at most 44. But pinning it down, that's the problem.
Why can't we just use computers to figure it out? Check all the possibilities.
The computational complexity becomes astronomical. Proving it involves solving systems of polynomial equations. For 5D, you're looking at determining if certain solutions exist for equations with potentially thousands of variables. It's beyond current brute force capabilities.
So for most dimensions, we're stuck with a range, a lower guess, and an upper limit.
Pretty much. We know from rough estimates, looking at volume, that the kissing number grows exponentially as the dimension increases. But the exact rate of that exponential growth, the base of the exponent, that's still a mystery.
There's this huge unexplored territory between the known bounds.
Exactly. It leaves so much room for future discovery, showing how a simple question about touching spheres can lead us to the frontiers of mathematics and computation. It's a beautiful example of complexity arising from simplicity.
Truly fascinating. Thank you for walking us through that. It really stretches the mind. And for everyone listening, if you enjoyed this deep dive into geometry's puzzles, please do subscribe and consider leaving a 5-star review. It genuinely helps us keep exploring these kinds of topics.